Stereoisomers, Conformational and Cis-Trans by Dylan, Steve, and Kevin. So what are they? Isomers are molecules with identical molecular formulas, while stereoisomers are isomers that have the same molecular formula and only differ in how their atoms are arranged in the 3D space. Newman and Sawhorse projections. So the Newman projection, or the one that looks like a circle, is the visual representation of a chemical from the front to the back, in which the atom at the front is represented by a dot and the atom at the back is represented by a circle. This representation can also be used to study cyclic molecules. Now, the Sawhorse projection, or the one that looks like a line, is the display of a molecule from an angle that shows the carbon-carbon bond at the middle of the molecule and can be drawn in the eclipsed or staggered conformation. Cis-trans isomers. So, for cis-trans isomers to occur, two conditions must be met. The first condition is that it occurs where you have restricted rotation somewhere in the molecule, and an example of this is a double bond, like shown on screen. The second condition is that it will be either in a cis or a trans configuration. So the cis configuration is when the same atoms or groups are on the same side of the double bond, like the right structure in the first photo, and a trans configuration is when the same atoms or groups are across the double bond from one another, like the left structure in the first photo. And now the effect of cis-trans on physical properties. Trans isomers have higher melting points due to their longer, flatter shape and better ability to fit together, while cis isomers have higher boiling points due to the fact that they are polar molecules, while trans isomers are nonpolar.
Now moving on to conformational isomers, so these are stereoisomers that are obtained by rotating molecules around sigma bonds. We see in the bottom left here for two orientations of 1,2-di-deuterioethane, where in the top the deuterium is located at the top and the bottom, where in the bottom image the deuterium is located both at the top from a rotation around the carbon-carbon bond. And it's the same for the image on the right for ethane, where you see different orientations of the hydrogen bonds can be seen from a rotation around the same carbon-carbon bond. And so from these rotations, there can actually exist a near infinite amount of conformational isomers. And so depending on the shape and orientation, different conformational isomers exist at different energy levels, though the energy required to rotate from one shape to another is actually relatively low. From this graph for ethane, we can see that the energy difference between the two most extreme forms is only around 3 calories per mole. So even at room temperature for ethane, there can be up to 10 to the power 10 rotations per second. And primary for alkanes, there are two main shapes for conformational isomers. One is eclipse, where the like groups overlap, and for this ethane molecule, if looking at it from the front, we can see that the hydrogen molecules overlap, where in staggered form they are more separated. And here are the Newman projections for these two forms. We see in the bottom for the eclipse form how the hydrogens are on top of each other, where in the top they're more staggered. And actually for staggered form, there are two more main forms called anti and gauche. And so in anti, the like groups are as far away from each other as possible. We see here 180 degrees, where in gauche, the like groups are a little bit closer, around 60 degrees away from each other, as seen in these two diagrams. And so for these two main forms, staggered is actually more stable than eclipse. This is because there exist repulsive forces within electron pairs and bonds. And so from the overlapped and eclipse form, it experiences more torsion strain. However, staggered form with the atoms away from each other, it minimizes these forces, so it's a more stable than eclipse.
Cycloalkane structure. Cycloalkanes are cyclic hydrocarbons. Carbons of the molecules are arranged in the form of a ring. Cycloalkanes are saturated. All of the carbon atoms that make up the ring are single bonded to other atoms. Cycloalkanes are made up only of carbon-hydrogen bonds and carbon-carbon single bonds in a ring. The smallest cycloalkane is cyclopropane. To find the chemical formula of a cycloalkane, use CnH2n. All of the cycloalkanes from cyclopentane upwards exist as puckered rings. For example, cyclohexane has a bench shape like this, looks like a lawn chair. There are cis-trans isomers in cycloalkanes without free rotation. Cycloalkanes in a cis formation have two constituents on the same side of the ring, whereas cycloalkanes in trans formation have two constituents on the opposite sides of the ring. Cycloalkanes give off a very high and non-favorable energy. Basically, the atoms create repulsion when near each other, which is called ring strain, and this causes an increase in energy which ends up stored in the bonds, which makes the entire ring unstable and reactive. Planar cyclohexane contains 12 pairs of eclipsed carbon-hydrogen bonds and is destabilized by these eclipsing interactions. The most stable form of cyclohexane is the chair shape, where the CCC bond is 111.5 degrees, which is very close to the optimal angle of 109.5 degrees. Cyclohexane is able to adopt the chair conformation the best, making it the most stable. Thank you for listening, and here is our bibliography.